Thanks for the introduction. So I'm happy to present some key value store studies with RDMA in this talk. Why we choose key value store? Because that's I found a very interesting thing if you look at the papers from or some articles from HPC area or from distributed computing area, right? Whenever you want to show RDMA benefit in HPC guys, and then they will show NPM numbers. Now, if you go to distributed computing area, you want to show RDMA benefit, typically you show either key value store or RPC, right? So that's why key value store is a very important data center workloads for RDMA networks. Let me explain why. So there's one reason for that is because a lot of people trying to get performance for big data analytics or storage, So these days, there's one concept called in-memory computing. A lot of people trying to move their data analytics jobs or pipelines on in-memory computing-based stacks. For instance, like they're trying to use Spark instead of Hadoop, right? So this kind of emergency of memory-centric computing systems or storage systems has become very popular for data center workloads these days. So one way to provide this kind of in-memory based storage systems is actually trying to use distributed key value store. This is just a very high-level overview of how you can construct or how you can deploy a distributed key value store layer on data centers. Typically, you're trying to aggregate a lot of memories, or I think we have some talks about persistent memory, right? Persistent memory can also be integrated, or even SSD, that's also possible, right? You're trying to aggregate them, make a very big memory pool so that a lot of requests or a lot of data can be cached in this layer, and then your application can access the data very quickly rather than go to backend database or storage systems. And then if you look at data center architectures, actually you'll see that once your requests come to the data center, you actually have a caching layer on top of database or non-SQL database to cache the query results so that you don't have to access the database very extensively. So as we can see that in order to get performance on distributed key value stores, typically you need to have very good design with your communication engine, because a lot of these daemons or services that they get collected with high performance networks. Not only for the like web analytics or web query, those kind of workloads, these days key value store has also being utilized by other kind of application scenarios. For instance, we summarized four kinds of application scenarios here. One is like SQL or graph database query cache, and then the other one is offline data analytics workloads. For instance, you are using key value stores to staging your data from HDFS to computation engine, something like that. Or even like a real-time analytics workloads, you are using some PubSub, those kind of messaging services. This can be implemented on top of key value store as well. And then the last one is very interesting these days. People trying to use key value stores as model surfacing, those kind of things. So you can query this model for your machine learning workloads. Now, this is just the application scenarios, but if you want to summary what kind of needs from these different key value centric workloads, we'll see that typically they need three kind of goals or must have, or at least better to have performance kind of things. For instance, for latency perspective, definitely we are trying to get the key value pairs or objects as fast as we can, right? So latency matters a lot in this case. Another two dimension is actually very interesting. One is server scalability. I think multiple speakers already mentioned that many workloads or pipelines, they need async kind of data flows or pipelines. And then also durability, like those, I think Tom and the other speaker already mentioned about persistent memory, right? That can be helpful as well. And the third dimension is about the resiliency, because for some workloads, yes, if you don't have cache data, you can go to the database, get it. But for some kind of workloads, if you use this cache layer or distributed key value store layer as a staging layer, then you don't want to data get lost, right? In that case, you still need to guarantee fault-tolerant support, something like that. And in order to achieve fault-tolerant support, typically you need memory-efficient design so that you can reduce number of copies, those kind of things. So now the question is, we have a lot of advanced devices these days in HPC clusters or modern data center architectures. Now the question is, can we exploit them in the best manner to achieve these goals? For instance, I believe many of us already know that a lot of kind of molecule-aware, pneumo-aware memory cache, key value store design, and then they also have GPU-based key value store design, FPGA-based key value store design, and then in this community, I think we are more interested with RDMA-based key value store design, right? But of course, SSD or NVRAM, those kind of things can integrate together as well. So with this, I want to present the three different kind of work or approaches we have done in our team to show that how we can really get the benefit from these three angles and how to utilize RDMA to achieve that. So the first thing, of course, through this, I want to show that why RDMA is so important and why those papers or those authors are trying to show RDMA is so beneficial for key value store applications. This figure actually gives you a very good answer. Like if you look at the breakdown numbers, okay. So there are the two graphs. If I stand in this way, then the right side one is when your data can fit in memory, okay. So basically means all your key value pairs can be cached in memory. And then the left side means if your data cannot fit in memory, then you have to evict some of them, right? And then you have to get the key value pairs from somewhere else. Okay, so let's start with, from the right side because that's the default scenario for many in-memory key value stores, right? They're assuming that all data actually cached in DRAM or something like that. So the left two bars is IPOB-based memory cache, set and get operations. If you look at the green, the breakdown one, if you look at the green part, you'll see that that's actually means client wait time. Basically means if I send a request like set or get, how much time I have to wait until this result come back. This essentially means a lot of time being consumed by the communication engine actually. And then if you bring RDMA into this picture, you'll see that okay, RDMA-based memory cache set and get or hybrid one basically means if you memory cache use both memory as well as SSD, okay? So we see that with RDMA, we can significantly reduce the green part, okay? That's the reason why RDMA can benefit a lot of in-memory key value stores. Okay, now if you go to the left side, like when data does not fit in memory. So in that case, what happens is in the application, you typically need to access database or some other persistent storage, right? You have load the data back to the cache layer and then you serve the requests. In that case, if you access the database, here the example is from MySQL. You typically need to send you need to consume around 2 milliseconds to load the one record back to the memory cache layer. So in that case, you will see that the gray part is significantly kill your performance, right? You have to spend a lot of time to access backend database. But if you have the hybrid memory cache design, which means you have SSD-backed key value stores, then you should be able to load the key value store much quicker than access database. So in that case, you can reduce a lot of latency. But if you compare the time between in-memory case and the not in-memory case, you'll see that they still have a big gap. For instance, if you look at the y-axis, for this side is like around less than 40 microseconds, but that side is around 500 microseconds. It's like 10x differences, right? So now the question is, can we propose some designs which bring this gap, which reduce this gap? Okay, even though your data actually stored in the SSD, but we are able to, through some approach, we're able to hide those latency and then give you near in-memory performance. That's the idea behind this work. So with this, what we see is that in many key value stores, including like memory cache, that their default API semantics actually is designed for in-memory or in DRAM cases. So which means I don't have to wait too much time. I want to do a memory cache set or get, I'm assuming that I will get the results very quickly. So that's why the semantic is blocking semantic. But actually, if you have SSD or persistent memory as the backend storage for key value stores, then your time to access your time to access P memory or the SSD is much slower than the DRAM, right? in that case, if you're still waiting for the request coming back, then your performance will significantly degrade, right? In that case, we are inspired by MPI community, right? We typically, in this case, we typically trying to issue some kind of long blocking operations. But unfortunately, in default memory cache, there's no this kind of long blocking APIs. So that's why in 2016, we proposed a work which trying to propose some kind of long blocking API semantic extensions to memory cache D so that it can match with RDMA semantics very well. For instance, if you want to access some key value pairs, you can issue a long blocking memory cache D I gate or B gate. In that case, RDMA actually happen in the background by the HCA so that you can do whatever you want in your CPU side, right? And then we also have the some kind of a structure like a request, and also we have corresponding API like a test and the wait, so that you can check whether this request finished or not. In that case. So with this, if you look at the performance again, this is the data does not fit in memory. The figure what I showed earlier. So the left part is still the original numbers. Only the color may be different. And then the key information in this graph is the right side. So as we can see that through the APIs, whatever we proposed in the last slides, we see that we can very efficiently overlap the SSD access. I believe if we change this part to PMAN, this also can be fully overlapped with our proposed designs. Then if you take this design into some kind of YSSP-based workloads, I think in these slides, we'll see that actually for no matter for read-only or write-heavy workloads, we have a good chance to do more overlapping in your applications. And then I think downside is about the read-only and the write-heavy workloads performance for the throughput perspective. We can see that the design we proposed can improve your overall throughput by almost 2.5x in many cases. So this is about how you can best utilize RDMA in some kind of hybrid key value store environment. Now the next topic I want to highlight here is about fast online erasure coding with RDMA. So RDMA can also, basically the information here is that RDMA not only benefit for performance, it also benefit for fault tolerance. Okay. So for some of you, if you don't familiar about erasure coding, here I gave a quick overview how erasure coding works from a theoretically perspective or a practice perspective. So this figure, the most right side one, actually give you the theory behind the erasure coding. This is a Redis-based erasure coding. It's very easy. I give you an encoding matrix. Use this matrix. Use this metric to multiply with your original data. Okay, and then I will generate some new matrix which the top part is still exactly same as your data matrix. Okay, only the bottom part actually we generate extra rows to represent some kind of parity chunks. Okay, if some rows get lost for some reason, okay, then we have a decode metric to re-multiply with your remaining data again. Okay, including data chunks as well as parity chunks. Then we can exactly recover your origin data. This is the theory behind the Redis-based erasure coding. Now how you can implement this or how you can deploy these things in the real system, basically the middle figure actually show like that. You need to decode your data to k data chunks plus m parity chunks, and then all the chunks will be saved to different kind of to different servers. Okay. And then if some server gets crashed or some data get lost, you are able to gather another k chunks again, then recompute on that or decode on that to get the original data. So now the question is, if you look from the performance or fault-tolerant support perspective, you'll see that if you compare erasure coding with replication, you'll see that the replication, of course, much simpler, right? It gives you good performance because you just write data and then you read the copy back to the computation engine, right? But for erasure coding, you always need to pay the penalty of the encoding when you write data and then decoding when you read data. So that's actually time-consuming operations. Now, but the benefit of erasure coding is that we can use less amount of memory or less amount of storage device to store same amount of data with the same level of fault tolerance guarantee compared with replication scheme. Now the ideal case, of course, is the blue cycle represented, right? That's the ideal case. Basically means you can achieve good memory or storage efficiency, but you also get good performance. Now the question is whether we can get this good or ideal case in our system, and also how to achieve that, whether high-performance networks can help on that or not. So we actually investigate into this problem. We have, in 2017, we have a paper in SDCS. We theoretically analyzed what's the benefit, what's the potential of utilizing RDMA to redesign the protocol of erasure coding. And we also analyzed whether you should do this erasure coding encoding operation or decoding operation server side or in client side. Okay, if you're interested, please refer to read this paper. We have very good modeling analysis, and the conclusion is that, first of all, you need the first design we proposed earlier. You need to use the non-blocking extensions and non-blocking APIs to try to overlap the encoding decoding operations with your communication phase. That's first information. Second information is that you definitely need good erasure coding libraries. Okay, there's a lot of erasure coding libraries available. For instance, you can use Intel ISA-based approach. You can use Mellog's erasure coding offloading-based approach. You can also use GPU-based approach. Okay, no matter which approach you're trying to use, try to select the best one to reduce time of decoding and encoding. Okay, and the third thing, of course, like I said, you need to see whether you should do the encoding or decoding server side or the client side. Okay, so we have implemented all these components in both Memcached client and also the Memcached server. We are trying to evaluate with them with different kind of combinations. Finally, we see that if you can do encoding in the server side and then do decoding in the client side, you'll get the best performance. Okay, we compared with different kind of electronic schemes with synchronized-based replication or asynchronous-based replication. Okay, we see that with SECD, we are able to achieve very similar performance and sometimes even better than the asynchronous-based replication scheme. For instance, we see that 38% performance improvement, like the green line shows. That's for I-set latency. For get latency, we also see similar kind of performance, similar to the asynchronous-based replication scheme. Now let's take a look. Take a look how about the recovery as well as the memory efficiency perspective. So when some data get lost, you have to pay the penalty of decoding because decoding is very time-consuming. And then we see that with our design, we are almost close to the asynchronous replication. For read, I mean, unless you have a very magic decoding approach, like zero overhead, otherwise it's very hard to beat the replication-based scheme, right? Replication is easy. I just find the replica which is still there. I just read it, done. But for decoding, you have to read some chunks and then come back and then do the decoding and then give to the application. But with our design, by hiding some of these latencies through the non-blocking operations, we are able to reduce this gap only like 27%. That's pretty good achievement, I think. But if you look at the left-sided graph, compared with the replication scheme, we can reduce your memory utilization around 56%. And also based on what kind of Redis-Solomon code you're trying to use, we can further reduce this kind of memory or story utilization compared to the replication. Okay. Now the question is, I present these things. What's the real application scenario, or how to utilize these techniques in real applications, right? So here I give one example, but I believe there are more examples can be found in many real applications. But this example, we actually inspired by some kind of systems like burst buffer kind of things. We are thinking that can this kind of key-value stores, enhanced key-value stores, be utilized or be leveraged to design some kind of high-performance burst buffer systems, okay, on top of PFS, especially for big data workloads. So let's take a look how people are trying to handle I/O problems in both traditional big data era as well as HPC era. So this is the traditional big data era, right? We are trying to the first or the main philosophy of those guys design their I/O schemes is based on data locality, right? I'm trying to schedule my computation task to the nodes which already has data, so that you can access data locally. That's the design philosophy. No matter Hadoop or Spark or other systems, they do things like that. But of course, there's also some other kind of design like Taekyang or Xiaoyi. They are trying to bring in-memory storage system, in the memory file system, into the big data community as well. So the idea is that I also trying to utilize memory as the storage device, and then if you can access data in local memory, that's very fast. But if you're not, then you need to load data back from the backend storage like HDFS or other kind of storage systems. This is how traditional big data guys trying to handle the I/O problems. But if you look at the HPC guys, how they handle big data I/O problems, it's based on fast parallel file systems or fast networks to access your data, right? So these days, people are also trying to use burst buffer I/O layer, like memory-centric storage system, to trying to handle your I/O request in this layer, and then stage back your data. But typically, in many HPC scenarios, there's no very big local storage device, right? So that's why this solution is very popular in HPC clusters. So with this, we are trying to think that, okay, if you need this kind of in-memory layer, and this layer has to be high performance, right? That's why you use it, right? You're trying to use an in-memory concept, and then you're using fast networks to access it. But in the meantime, you also need a fault-tolerant, right? You don't want your data stored in this layer, and then if some power is gone, then your data is lost. You definitely need the fault-tolerant support. Okay, so this is a perfect scenario how you can utilize RDMA plus erasure coding plus whatever I presented earlier together to build a prototype on top of RDMA networks for big data workloads on HPC platforms. So we have a small system or prototype system called Bodio. We present this idea in Big Data Conference 2016. We are trying to see that through our design, whether we can beat some kind of performance numbers, even when you have data locality support, okay? So we are trying to contrast our design with different kind of schemes. Let me explain them one by one, okay? The first one, definitely Lustre Direct. Okay, you directly access your Lustre from your computer nodes. That's one way. Of course, your performance will not be good if your Lustre is bad, right? But if your Lustre is good, essentially, if a lot of clients trying to access it, you still see the performance bottleneck over there. Okay, then on top of that, you can deploy Xiaoyi or Taekyang, those kind of systems on top of Lustre. So in that case, of course, if you have data locality, definitely you just access your data basically from your run disk, something like that. Okay, so that's why you'll see the green bar is very, very high performance. Okay, you get a good performance because of data locality. But because your memory still sometimes not enough, right? You still have to upgrade your data from backend storage. Then the Xiaoyi performance will significantly goes down because they don't have RDMA support. You have to use TCP-based approach and then get data from backend HDFS or Lustre. So that's why your throughput goes down significantly. But if you look at our design, no matter Bodio based on asynchronous replication or based on erasure coding, whatever we presented earlier, we will see very stable performance almost. Okay, much better than Lustre Direct, but also much better than Xiaoyi if there's no data locality access. And also we see that with our erasure coding design, we see very negligible EC overhead. This means that we actually can bring EC approach to the real storage system now. But if you go to the right side, this like Hadoop read throughput performance. This one, the left side is Hadoop write throughput performance. We see that interestingly, no matter which case, we are always win in all these tests, almost like a 7x performance improvement for that. So we also run some Hadoop workloads from throughput perspective. We run write and read on top of the Bodio design compared to Lustre Direct. We see almost 7x or 3x performance improvement depending on different scales. So we have, I think time's there. Okay, we have made these solutions available in our HiBD website also. So this RDMA-based Memcached we have maintained it for multiple years. We keep merging them to their new versions. We also develop some benchmarks. If you want to try with these solutions, please go there and download that. Okay, with this, let me conclude my talk here. So this talk, I'm trying to present why key value storage is important for data center or cloud computing guys, and then what kind of key issues are there, especially not only for performance, but also from resilience perspective, as well as what kind of real scenarios you can utilize these kind of designs. So we present a holistic approach to efficiently leverage HPC resources, especially hypervisor networks. But in this talk, I only introduce how to utilize RDMA to improve these designs. But actually, we have ongoing work with trying to use Mellog's EC offloading approach to further enhance the performance. Okay. So we present the RDMA aware non-blocking designs for key value stores. We also co-design with the erasure coding algorithms, and then trying to get a good performance for that. So our library is available again. So please feel free to try that. Thank you. I would be happy to take any questions if you have. Okay, I think this is all for today, right? Thank you.